Welcome to part 2 of measures of variability. Last time, we talked about two different measures of variability, the range and the interquartile range. Today, we're talking about a third kind, one that's more complicated, but also more popular, and that's the standard deviation. But before we get to that, let's recall the two probability and statistics classes that we talked about last time, Class A and Class B. These two classes both took the same test. In Class A, we had a situation where everyone got a 75. In Class B, half got 50 and half got a 100. And we said that just looking at the class average of these two classes, we can't tell the whole story because both of these have a class average of 75. And so we want to look at measures of variability as a way of telling a bigger picture story about these data sets. And with the range, one of the complaints is that it only concerns itself with two data points from the entire data set. The largest value and the smallest value. No matter how big that data set gets, those are the only two data points that are going to be considered. The interquartile range does things a little bit better in that it only throws away the top 25% and the bottom 25% and considers half the data set that lies in the middle. But that's still only half of the data set. Maybe we can come up with a measure of variability that takes into account every point in the data set. And that's what we want to look at today. So to make our Class A and Class B example a little easier, let's go ahead and say that there's only 6 students in each class. All right, so let's just make a table. So for Class A, we can write down their scores. Right, this is pretty easy. Class A is a situation where everybody gets a 75. So we have a 75, 75, 75, a 75, 75, and wait, a 75. And so one way of answering what is variability, or how do we measure variability, is this idea of whenever we find a typical value, does the data in the data set stay near that typical value? Or is it all over the place? So maybe we can address variability as what happens if I subtract away a typical value from each of these scores. So if I subtract typical value, call that the TV, then each one of these, our typical value was a 75, that was a class average, would be 0. And so if we add up all of these differences, we get 0. And in some sense, we're saying that this says that there's 0 variability. And that's kind of what we said last time, that if everybody gets the same score, there's really no variability there. But let's look at what happens if we approach this from the situation of Class B. So with Class B, we said that half the students get 100, and half the students get 50. Now again, we can go through and we can subtract away our typical value. And again, we said that the typical value here was a class average of 75. So if we subtract 75 away from each of these 100s, we get 25. And if we subtract away the typical value of 75 from 50, we get negative 25. And if we add all these up, we get 25 plus 25 plus 25, which is 75, minus 75 minus 75, or minus 25 minus 25 minus 25, which takes us to 0 again. Kind of looks like there's no variability here again. That's not true about Class B. We said class B has lots of variability. So this in itself is not a good way of measuring variability. The problem being that being 25 over can cancel out with being 25 below. But both of those are distance away from the typical value. So we want both of those to count. So the question is, what can we do to make sure that being above and below both count towards adding to our variability? And that's what the standard deviation does. And we're back. So we've got class B, and half the class has 100, half the class has a 50. We've already subtracted away the class average from each of these, and we got 25, 25, 25, minus 25, minus 25, minus 25. And when we added those up, we still got 0. So we said, well, we want to make sure that being too large or larger than the typical value counts just the same as being too small or below the typical. So the way we can get around that is by, instead of looking at just what happens when we subtract the typical value, let's subtract the typical value and then square it. Because whenever we square a number, a positive number stays positive, and a negative number becomes positive. And so this way, all of the values are positive, and they're all going to count the same. Minus the typical value, square all that. Then 25 squared is 625. But negative 25 squared is also 625. And so now being larger than the typical value counts just the same as being smaller than the typical, which is what we wanted. And so the next step that we want to do is we want to try to figure out a meaningful way of taking these distances, coming up with a measure of variability. And so to do that, let's look at a less contrived data set. All right, so we're at standard deviation. Now, let's start with a formula that's going to look intimidating. But whenever we compare it to what we just talked about with Class A and Class B, hopefully it becomes a little easier. So for a sample, we have a formula for standard deviation that's S is equal to the square root of the sum of x minus x bar squared divided by n minus 1. Now, in this formula, the x value stands for the values in our data set. X bar, if you remember, stands for the sample average. And then n in this case is going to represent the total number of elements in our sample. And why this is n minus 1 is beyond the scope of this course, but you're just going to have to trust me on this. So the first thing that we need is our x bar. So we have a data set and we need to know what its average is. So in this case, x bar is equal to 2 plus 4 plus 1 plus 5 plus 3, all divided by the 5. And in this case, we get 6, 7, 10, 15 over 5 or 3. So that means our sample average here is 3. So we start the table just like we did with looking at our classes. Let's start with our x's. So our x's in this case are 2, 4, 1, 5, and 3. And then let's look at what happens when we take x minus x bar. Right? So again, we're just asking how far away is it from the typical value. So 2 minus 3 is minus 1. 4 minus 3 is 1. 1 minus 3 is minus 2. 5 minus 3 is 2. And 3 minus 3 is 0. But if I add these up, you'll notice that the minus 2's would cancel, the 2 and minus 2 would cancel, 1 and minus 1 would cancel, and the 0 wouldn't add anything, and we would still get a sum of. So in the formula, we have x minus x bar squared. We do the same thing that we just talked about, x minus x bar squared. So we take each of these and we square it. So negative 1 becomes 1, 1 becomes 1, negative 2 becomes 4, 2 becomes 4, and 0 squared is just 0. Now, this symbol right here says that we add all that up. So we come down here and we add this up, and this gives us n. And so plugging this in, we get that the standard deviation is equal to 10 over 5 minus 1, and then the square root. Gives us 10 over 4 square root, or the square root of 10. And this is our standard deviation. Now, I'm hoping that the Class A, Class B example provided some illustration for what we're doing. Basically, we're going through and we're calculating what happens when we calculate the distance from each data point to the typical value. We're squaring it to make sure everything is positive and that they all count. And then we're dividing by what's close to the total number of points in the data set. So it's almost like we're taking an average. And then to kind of reverse the fact that we squared everything, we take the square root. And like I said, the n-1 is beyond the scope of this course. But there are two formulas for standard deviation. This is the formula for a sample standard deviation. So if your data is a sample, is a part of a larger population, then this is how you calculate the standard deviation. For population data, if you actually have data for the whole population, then you can calculate the standard deviation a little differently. So population standard deviation is denoted with a sigma, and it is the square root of the summation of x minus mu squared all over n. And we use a little bit different notation here because it's population standard deviation. Mu stands for the population average, and the capital N represents the total number of elements of that population. And so that's useful for you to know, but because this class we're mostly going to be working with sample data, this is the formula that we're generally going to use in class. So this is the one that we want to pay more attention to. So, till next time.